Good morning, everyone. Um, First, I would like to thank the chairperson, the vice chairperson, the treasurers, the committee members, and the staff of IPI for giving me this opportunity. And so, when we look at the 30,000 feet, the overall broad picture of what we see from that level towards what's there on the ground in the automotive industry, they always talk about a few things, maybe 8 to 10, that are very important for the automotive industry. They talk about artificial intelligence, big data and analytics, HMI, human machine interface, Internet of Things, safety, connected vehicles, alternate fuels, and additive manufacturing, and so on. There are a few more things. That's the trend that has been there in the last 10 years in the automotive industry, and it is going to continue that way. The paradigm shift that was mentioned is mainly happening on the connected and safety side, alternate fuels, and then you have the comfort and convenience of what the customers want. Okay, so this is the top view. So you might ask, what is that I can contribute to this trend? Well, I would say that if you are in the plastic industry, this is the most exciting and amazing time to be in, particularly in the automotive industry. With changes to the paradigm shift that is happening in fuels, the alternate fuels, you might think that what is the plastic industry contribute? Is the business that I'm doing is going to go down? Well, actually not. There is plenty of opportunities at the bottom. Okay, so from 30,000 feet, if you go down a little bit, you can break it down to connected and safety, right? That is one. I'm combining connected and safety as one. Otherwise they have two, connected and safety separately. Then you have the comfort and convenience, what the customers want, right? We are talking about the perceived quality. Is it too plasticky? That's one of the things that any common person would say if they look at a car or a two-wheeler, right? The perceived quality aspect of it, the appearance. Does it look plasticky? Does it feel plasticky? The smell when you get into the vehicle, that is the thing that you observe, right? The sound that is coming out from outside to the vehicle, or from the vehicle to vehicle, or the buzz rattle that is happening in the vehicle, right? So these things are very important for customers. So when we talk about designing a vehicle, we need to take care of what the customer wants. And nowadays the want is increasing because the people who are traveling all over the world, they can see the quality they get in other OEs and other countries and compare it with what they can get in India, right? So that is a good thing for the plastic industry, because you can always make the material better in terms of appearance, touch and feel, and so on, to improve the customer and the experience the customer has with the plastic parts. And then comes the most important thing. It's the environmental sustainable regulatory materials, right? So here you have all the things that are combined in alternate fuels, the fuel efficiency, weight reduction, the CAFE norms, and the sustainable materials, right? So we talk about CO2 emission, the GHG levels, right? So that's one step below what we looked at from the 30,000 feet. Now, how do we break this down? How can a small player, right, might be thinking, how do I contribute? Well, if you guys know, there is a Nobel laureate, Dr. Richard Feynman, and he wrote a letter to one of the students, and he mentioned that no problem is too small or too trivial if we can do something about it. Okay, so if you are a small player or if you are a big player, doesn't matter. It's about how you can contribute, how much you can contribute to the innovation, to the regulatory requirements. That is very important when you talk about the automotive industry. Okay, so now let's take a step back and see how traditionally cars or passenger vehicles were made. Mostly it was steel. If you guys remember, it's still there. Mostly it is steel with a bit of aluminum sprinkled here and there, right? But 70% is mainly steel, mild steel, advanced HSS, ultra high, steel. So you have those things which make up about 60 to 70%. But do you guys know that in 1904, aluminum was used for panels, body panels, to make four-wheelers? That is more than 120 years ago, right? And it took a long time for some of the companies to implement aluminum enclosures. So when you are in the plastic industry, you have to look at what the other players are doing. It's very important. Then only you will be able to come up with alternatives. You can come up with innovation. Okay, so you cannot just focus on, okay, I'm doing PP and okay, what can I do to convert PA to PP, right? But if you open up a little bit more, okay, what can I replace metal to plastic? You need to understand what the metal industry has done. They have done an excellent job. When aluminum was slowly taking over, the steel industry came back with so many new grades where you can make a thin wall, okay, with very cost effective solutions. So the same thing has been translated from aerospace, aircraft industry to automotive industry. If you traditionally take an aircraft, it's about 70-80% is aluminum. I'm talking about the old generation. But I think the A320, I think, was made with 50% composite. And most of the interiors anyway are with plastics. Okay, so look at what the other industries are doing. Can we learn something from those industries? How do we bring those technologies and make it worthwhile for the plastic industry? That's something that we can look at and bring in the new innovation that we are talking about. Okay, so when the automotive industry talks about lightweight, it's not just plastics and composites, right? They always look at the ultra high strength steel, aluminum. Different grades are there within aluminum. And one of the stories a few years ago, I think you guys must have seen, one of the EV manufacturers, Tesla, they eliminated about 70 parts, steel parts, which are welded together in the body shop, and converted everything into one or two aluminum die-cast product by eliminating so many of the operations, so many of the robots that is required, the time that is required in the body shop. Actually, our industry, the plastics and composites industry, has also done something similar, right? whenever we talk about can we replace metal with plastic or composites, what is the first thing we do? We don't go for A to B replacement. It will never work. Plastics or composites can never compete with steel in terms of cost. What is done? You try to consolidate, you try to integrate the parts. Can I eliminate 5 to 6 operations? Can I reduce 5 to 6 parts to one? The consolidation that happens at that place is what will give the advantage in terms of capital investment, in terms of reducing the weight. And by the way, it's already done. There are hundreds of examples where metal has been replaced by composites with consolidation and cost reduction and weight reduction. Okay, I think maybe 3 years ago, Teijin Automotive introduced one type of nylon material which is reinforced with carbon fiber, Ceribo, and they replaced the pickup box structure that is there in the GMC pickup truck, and they reduced about 40% weight saving, leading to cost saving as well. Okay, so there is a plenty of opportunity here when we go from metal to plastic or from plastic to plastic. For example, the rooftop that we have on some of the I think it's a Jeep vehicle is made of SMC, right? So when you look at the Thor that is currently in production, that is a 15% glass filled polypropylene blow molded. Okay, going from a traditional SMC to PP based material. Again, this is plastic to plastic, where you can have weight reduction as well as cost reduction. As Mr. Balaji was saying, we talk about cost reduction all the time, right? But as engineers, you have to convert the customer requirements to engineering requirements very clearly. If you don't understand and if you don't feel what the pain points are, you will not be able to convert them into engineering requirements. And without engineering requirements, you will not be able to make a material, a part, or an assembly. Okay, so as you guys, some of you are material suppliers, you have the most knowledge in compounding, in basic formulation. Nobody has to teach you. But when you do make a compound, it's very critical that you understand its application first, right? So when I say application, I'm talking about what the customer wants, what is the reg affairs, the regulatory requirements, what is the business requirement of it. So if you do all these three, your engineering requirements will be taken care of. So when you convert this to a material to part that comes to life, then you have the satisfaction. You don't want to make a lot of grades, a lot of innovative projects which don't see the application. It's of no use. Nobody wants that. So have a very clear strategy on designing a material and then to designing a part. Okay, so that is that aspect on how we can consolidate parts to reduce cost and reduce weight, as well as going for lightweight technologies, not only from metal to plastic but plastic to plastic. So we know that there are a lot of materials and processes that are available for plastics and composites, right? We can talk about GMT, long glass fiber, SMC, BMC, carbon fiber reinforced plastics, and accordingly we have injection molding, compression molding, high pressure RTM, hand layup. There are so many technologies available, how are you going to map the material to the process in the initial stages is very important. That's where your innovation comes in. Can I make it thin-walled part? I remember maybe 10 years ago, an IP retainer was made with long glass fiber PP with 2 mm. 2 mm, this was more than 10 years ago. So how do we make a material that can go thin wall but meet the performance, the durability, and the aesthetic requirements that the customer wants, right? So this starts with the material and design. So the key thing is, if you are a design engineer, you design for that material, correct? You don't replace steel design, and vice versa with a plastic design. You have to design for that material, okay? And when you do the design verification, when you are in the design verification phase, you need a lot of data for the composite or plastic materials so that you can feed in and see how the design is behaving, right? So that actually is a very critical stage, because if you don't know what your material is made of, what it can deliver, then the design is going to change. Whether it's a 2.5 mm or 3 mm will be very dependent on where you start with your material properties. So that is another customer requirement on how to reduce weight or cost. So most of the, again sticking on one more example on the application part of it, which is very important for me as an OE, is all the body panels, right? Again, traditionally steel and then aluminum closures are there in practice now. But if you look at some of the vehicles that have maybe 50-60,000 per year, the volume, or 100,000, some of the niche vehicles, they have composites, SMC. Okay, SMC has been there for a long time, right? So is there something that you can go from thermoset to thermoplastic and still meet all the safety, crash, and the requirements that go with it? Okay, so if you look at, let's say, Corvette, all the body panels are made out of SMC. Okay, but if you go out and look at probably a Bajaj Qute, that is polypropylene. Okay, the old Smart 42 was made with PCPBT at one time, as for the panels I'm talking about, and then they converted to 20% talc fill PP. So application wise, there is a lot of opportunities, whether it is ICE or EV or plug-in hybrid, whatever the thing is. There's plenty of opportunities to convert. The same way, you can also innovate on the process side, meaning instead of doing regular injection molding, can I do blow molding? Can I do compression molding? Can I do thermoforming and achieve the same properties, the same paintability, the aesthetics? Can I get it? Okay, so on the processing side. And then when you have done this, meaning the material is made, the data is collected, high strain data, rate data, crash data, everything is collected. You do the simulation, the design is frozen, then almost 18 to 24 months are gone. So one thing that is happening in the industry now is there is no time for 24 months. Can you get it done in 6 to 12 months? That's the time we are talking about. On the product level, that means on a material level, it has to be 3 to 6 months to generate all the data, have an initial check for the final application. So what about a lot of talk is going on nano composites, right? So when we talk about it, be specific, make it functional, don't make it as a talc replacement. Again, the same thing, steel to plastic, talc to nano, it can be anything, nano clay, whatever it is, doesn't make sense. Make it functional. Am I making it better by reducing 20% weight? Does the customer need that? Is it better in terms of paintability? Does it have better thermal properties, mechanical properties, electrical properties? With so many requirements coming from the EV industry, right? You need, thermally conductive plastics. You need good electrical properties, whether it is CTI, RTI, dielectric strength under humidity and high temperatures. Does my plastic, can it withstand 1000 to 1200 degrees C for 5 minutes? The materials are available. Nylon based, PP based materials are available. So when we talk about the EV portion of it, you have the motor, right? Again, the stator and the rotor cover can be made with plastics. And some of the things that I mentioned, high temperature, better electrical properties, better thermal properties, all these things come into picture. Are you guys able to hear me or? Okay, all right. So we'll continue because of the time. So, and then you have the entire battery pack, right? If you open it, you'll see plenty of opportunity again. You have the battery cover, you have the cell holder, and how do you have the cell divider, right? The plastic. Okay, and all the connectors, right? Again, plastics. Okay, so look at what the plastic industry can do, what the composite industry can do for these applications. Again, what we are looking from OE standpoint is we want something that has higher, I'm using the relative term here, okay? Not just high, I'm saying higher, meaning maybe 50 to 100, or it can be 1000 to 1200, okay? Relative term here. Higher temperature, high CTI, RTI, combination of these with humidity and thermal playing a role. Good chemical resistance, and the properties don't, mechanical properties, electrical properties don't deteriorate for 2000 hours much, not 2000 hours, sometimes it will be 3000 hours, okay? So these are some of the challenges that we have, and this is actually the trend in not only EV but also ICE, and it's happening where you need better materials. So when you make a material or you make a process, make sure you have the data, okay? As Deming once famously quoted, it's quoted everywhere, right? In God we trust, everyone else bring data, okay? Because if we want to make a decision faster, without data, you'll be making a gut decision, and if you have experience in that field, it works. If you don't, then you will have to make 1 or 2 iterations, and that is where you lose time. When you get into a loop of make a material, mold it, test it, fails, again you have to start. But you have enough data, we can do the screening upfront, eliminate most of the things we can do as rework and have the product in the market a little bit faster. Okay, so these are the things that I wanted to cover in sharing my points, my experience, and my things that I think is very important for the OEM. That is the perspective, and this is applicable for all industries. And if you are in, let's say, I'm in packaging, what do I do? What is the opportunity, right? There is plenty again. Maybe we can work something out on where the the micro plastics are not going to the water stream, right? Or it's not getting on the soil, right? So there's plenty of opportunity again. Okay, so finally I would want to have